Musical texture can often be a perplexing concept for musicians. Most music involves multiple simultaneous musical streams, which are distinctive melodic or harmonic lines. It can be difficult to distinguish the different streams and how they interact with each other. This is what makes the idea of musical texture incredibly convoluted. With our emerging research, Dr. Jonathan D'Souza and I have been experimenting with a quantitative approach to conceptualizing musical texture. The most common method for texture analysis has been manually observing and listening to a piece and assigning it to one of these four basic textural categories. Monophony, which is a single unaccompanied melodic line. Any number of instruments can be involved as long as they all play the exact same line. Polyphony is described as two or more independent lines of equal importance that are played simultaneously. Homophony includes one predominant melodic line with other subordinate lines that serve as accompaniment to the main melody. And heterophony is known as one melodic line played concurrently with one or more variations of itself. The melody can be varied with different rhythms, tempi, or other embellishments. Unfortunately, manual texture analysis has various complications. Some music may contain elements of multiple textural categories, texture rarely remains constant throughout a piece of music, and the category definitions are somewhat arbitrary, leaving room for personal interpretation. The music theorist David Huron offers a different approach to these categories. Huron states that there are two main parameters that allow humans to determine if a stream is the same or different in relation to another stream. These parameters are onset synchrony and pitch comodulation. Onsets are simply the beginnings of notes. If the notes of two different instruments consistently begin together, or in synchrony, then we are more likely to hear those instruments as belonging to one musical stream. Pitch comodulation analyzes if the pitch contours of two different lines rise or fall in conjunction with each other. Simply put, when two voices have the exact same rhythms and pitch contours, we'll most likely interpret them as the same musical stream. As these differ, we begin to notice two separate musical streams. Huron assembles these parameters into a two-dimensional graph called a texture space, with pitch comodulation as the x-axis and onset synchrony as the y-axis. The axes range from 0 to 100%. Each quadrant corresponds to a different texture type, and each corner represents the absolute form of that specific category. This graph allows us to observe the fluidity of textural categories as pieces rarely reside in the corners. In an attempt to analyze texture using this graph, a previous USRI student created some Python code that computes these two parameters. This code is applicable to any music that can be transcribed into Western notation. To calculate onset synchrony, our code determines the number of onsets shared from one instrument with respect to the others in the piece. For pitch comodulation, our code uses windows, which are small definable segments of a measure. It looks at all parts in this window, creates an average pitch for each part, and compares the pitch motion from window to window. Our specific code outputs 0 for contrary and oblique motion, and 1 for similar and parallel motion. Here's a quick reminder about these four main types of pitch motion. When one pitch remains the same and the others move in any direction, the relationship is called oblique motion. Contrary motion occurs when both of the pitches move in opposite directions. If the voices move in the same direction, it's called similar motion. And lastly, there's a specific type of similar motion called parallel motion. In this case, the voices also preserve the interval between the notes as they move together. For both onset synchrony and pitch comodulation, our code averages all the detected values per instrument to provide a percentage value, which can then be plotted on the graph. Thus far, we've applied this code to investigate two main topics: texture in a set of works by J.S. Bach, and texture in selected classical string quartets. The first study looked at 60 works from Bach consisting of 30 randomized chorales and 30 keyboard works, more specifically his 15 two-part inventions and his 15 three-part sinfonias. These sets were chosen because the inventions and sinfonias are largely regarded as polyphonic works, and the chorales are normally considered homophonic. Let's take a preliminary listen to an excerpt from a chorale and compare it to an excerpt from a sinfonia. Our Our statistical analysis showed that the 3-part sinfonias had significantly less onset synchrony than the 2-part inventions, but there was no significant difference for the pitch commodulation. This means that the sinfonias are considered to be more polyphonic than the inventions, but mostly due to rhythmic aspects. When also considering the chorales, we saw that they had significantly higher levels of onset synchrony in comparison to the piano works, but again, differences in pitch commodulation were statistically insignificant. Looking back at Huron's texture space, we can see that onset synchrony is the only parameter that influences the difference between homophonic pieces and polyphonic pieces. Thus, the lack of change in pitch commodulation is justified. Also, these results are consistent with our hypothesis of the choral works having higher onset synchrony in comparison to the keyboard works. Going back to the listening excerpts, you should notice a significant difference in the amount of simultaneous rhythms. Overall, this endeavor gives us insight into how Bach would alter his compositional style based on the genre he was composing for. The rhythmic synchrony of the chorales encourages participation and congregation, whereas the rhythmic complexity of the keyboard works encourages flexibility in a single player's technique. Our second major study involved analyzing onset synchrony levels in the opening sonata form movements of select string quartets from Beethoven, Haydn, and Mozart. Our main purpose for analyzing these movements was to compare the sections and subsections of sonata form, as they're traditionally either considered stable or unstable in many ways. Our hypothesis stated that the unstable sections would yield lower levels of onset synchrony in comparison to the stable sections that are conventionally homophonic. After analyzing these works, it was determined that onset synchrony is significantly lower in developments in comparison to expositions, but significant differences in transitions were inconclusive. We also came across other interesting information. While developments were all similar in onset synchrony, we saw significant differences in how the 3 composers approached synchrony in the exposition. Let's listen to a movement that yielded high levels of onset synchrony. This specific piece also demonstrates how quickly textures can change. Follow along with the on-screen texture prompts. We can compare that with this excerpt from a Mozart development, which uses less onset synchrony to contribute to this section's instability. The significance of this study allows us to see how texture interacts with form and how composers treat formal sections differently in their own unique compositional styles. The future significance of our current method of analyzing musical texture opens up many possible avenues for research. With texture, researchers can examine multiple musical implications such as common composer, genre, and performance practices. We currently have a few future projects planned. One study will look at textural practices in several different types of large ensembles, such as the Baroque orchestra, the classical symphony, a 40-part choir, the Balinese gamelan ensemble, and the jazz big band. Another study will analyze Felix Mendelssohn's string octet composition to see which instruments tend to share material the most. This could potentially inform performance practices such as optimal seating arrangements for that specific work. Eventually, we'll be using this code to look at texture from the lens of social network analysis and complex adaptive systems. Using the data from our preliminary code, we can create social network diagrams such as these to show how instruments interact with each other and contribute to the musical conversation. This could demonstrate that texture is an emergent property composed of multiple adaptive elements with no commanding force. In summary, our research can help clarify the ambiguity that surrounds musical texture analysis. Analyzing texture with a quantitative approach can give us significant information about many topics, such as the styles of past composers, genre organization, performance practices, and potentially how the social interactions in ensemble music connect to our larger societal systems. Thank you for watching.